Today we're going to talk about tangential velocity and tangential acceleration. So first let's look at tangential velocity. That is the linear velocity of an object moving in a circle. Remember, we talked about linear velocities before. We measured them typically in meters per second. Okay? But this time the object is not moving in a straight line. Instead, it's going to be moving in a circle. Okay? So we're going to look at that in a little more detail. So let's compare back. Okay? Let's look. We've had before, a person is moving along, okay, with a linear velocity, a constant linear velocity, like 5 meters per second or so, okay. Then that person could be running along, okay, in a nice straight line, and they're moving at a velocity of 5 meters per second, okay. So that means the distance that they move each second is 5 meters, okay, and it stays the same. Okay, they move 5 meters every second. If I drew a velocity vector in here, okay, it would look the same for each one. Okay, the velocity vector would be pointing in the same direction and would be exactly the same because it's a constant velocity of 5 meters per second. Now let's go ahead and translate that to somebody who's running in a circular track. So maybe they're still moving at 5 meters per second. All right. So now we got this person, okay, and they're moving along, and they're going at a nice constant speed, okay. So these should all be the same length, but I'm not going to call those x's because we use x to represent a nice straight line. Instead, they're moving along in a path that is a circular path, so we're going to call these arc lengths. So arc length 1, arc length 2, and arc length 3. Okay, but similar to up here, where these were each 5 meters, okay, these are each going to be the same distance. Okay, so it's very similar. If we draw our velocity vector, okay, they are going to all be the same length because they're going the same speed the whole time. However, you're going to notice that the direction the velocity vector is pointing changes. Okay? Another thing to notice about this velocity vector is the direction that it is pointing is tangent to the circle. So if this is the circle and we draw this velocity vector, it's tangent to the circle. Well, what does that mean? That means that this velocity vector intersects the circle at exactly one point. Okay? Only touches at one point, and that point is perpendicular to the radius drawn to the point of intersection. Okay? So this is why we call it the tangential velocity. The direction is always tangent to the circle. All right. Again, it's a vector, direction, tangent to the path, symbol v sub t, okay, the tangential velocity. The units are in meters per second, just like our previous linear velocities were in meters per second. And then we've got the equation. So let's go ahead and look at the equation. Okay, we had this equation from before. The arc length is equal to the radius multiplied by the angular displacement. Well, if I want to know a speed, I need a distance over a time. Well, this is a distance here in meters. I need to divide by a time. But if I divide one side by a time, I need to divide the other side by a time, so that we're doing the same thing with both sides of the equation. A distance divided by a time, here we're going to get our tangential velocity. And that is going to be equal to the radius multiplied by the angular displacement over time, which we defined earlier to be the angular velocity. So our equation is going to be the tangential velocity is equal to the radius times the angular velocity. And you need to be careful. This equation that we use to derive from, the angular displacement needed to be in radians. So therefore, in this equation, we must be in radians. Okay, so our angular velocity needs to be in radians per second. All right, let's go ahead and look at our tangential acceleration. Tangential acceleration is the linear acceleration of an object moving in a circle. Okay? So again, we've got this object moving in a circle. So we've got a person running around a track again. Except this time, that person is going to have a tangential acceleration. So they are going to be speeding up. So maybe they go that far in the first second, and then they go farther in the second because they are speeding up, and then even farther in the third second, because again, they are speeding up. So now, these arc lengths are not the same. They're getting greater as we go along. Okay, so what does that mean? Well, if we drew in our velocity vector, it would be again tangent to the circle at that point, but now it's going to be getting bigger in magnitude as it goes around. Okay? And what that also means is that our acceleration is in the same direction. Okay, we're accelerating the same direction of the movement. So our acceleration is also tangent to the circle, and that's again why we call it our tangential acceleration. So let's go ahead and see if we can derive the tangential acceleration from another equation. Well, we just said the tangential velocity is equal to the radius times the angular velocity. I know that velocity over time gets me an acceleration, so tangential velocity divided by a change in time will get me a tangential acceleration. And that, I need to do the same thing to both sides. I need to divide the right-hand side by delta t as well. And I notice that this is my angular acceleration. You're going to see a similar pattern going here, okay? And you'll also notice that, again, we derived this equation from that one, and in this equation we need to be in radians, so here we also need to be in radians. Our equation is going to be our tangential acceleration is equal to our radius multiplied by our angular acceleration, and again, we must be in radians. Okay, so our angular acceleration needs to be in radians per second squared. Okay, you may have noticed a pattern with our equations. Our arc length is equal to the radius times the angular displacement. Our tangential velocity is equal to the radius times the angular velocity. Our tangential acceleration is equal to the radius times the angular acceleration. So you notice that this radius is simply kind of acting like a conversion factor. Okay? A couple other things to take note of is in all of these equations, we need the units to include radians. Okay? Radians per second squared. Over here, we'll get the units that we had similar to before. Okay? Meters per second, and meters per second squared.